Online, you should be able to go ahead and share your screen. Xiaolong, sorry.
Okay.
And Xiaolong, Federica requests if you can turn on your camera if possible.
Okay.
Wonderful.
You see my screen?
Yes, we can see your screen. So if you put it in slideshow mode, we should be ready to go. Wonderful.
Okay.
Great. So next speaker is Xiaolong Li. Take it away, Xiaolong.
Okay, then thanks again. Thanks for having me again. So as we making preparations for the Rubin LSST, perhaps the most exciting thing is the Rubin's ability to discover the new phenomena, the phenomena we have never seen before. Like the Rubin's ability to making those discoveries will depend on its observing strategy. It's currently being designed. How can we make sure the observing strategy is not prevent us from making new discoveries? So we answer these questions by preparing two articles. The first article focused on time domain, and the second one focused on the proper motion. Evaluation of the ability to making discover true anomalies is a challenging task because it requires a model-independent approach. The new phenomena, by definition, is we don't know what the new phenomena looks like. So we approach this problem by explore the completeness in feature space, in the observational feature space, and also the volume explored by the Rubin LSST. So the observational feature space include the color and the color change, brightness and the brightness change. For the volume, this include depth, footprint, and the star density. Rubin team have developed hundreds of simulations that vary by varying the parameters like the observing time, meters, so on. And they also developed the metric analysis framework to evaluating the performance for each science case. And under this framework, our figure of merit is a linear combination of 5 metrics. This is the change of the brightness, color, depth, footprint, and the star density. In this plot, it shows the peak brightness of non-transient against characteristic time scale. From this, we notice that there are non-bias in the short time range and also long time scales. From short time scales is specifically the minutes to hours, and the long time scales for several years. But Rubin have the potential to access both those skills. So we pay attention to these time skills. And for the color, our algorithms goes as follows. For colors, we consider the observations in pairs of different features. For different features, we measure all possible time gaps between each features and select time gaps within 2 days as a reliable measurement of the color. And then we measure the similarity between the histogram distribution for each feature pairs, and measure the similarity between the distribution and with the ideal distribution. and sum over all filter pairs, and then weighted by the number of visits as the figure merit for color. For the brightness, we use similar algorithms, but extend the time gaps from minutes to 10 years in a logarithmic scales to give more importance to the short time range. And we also weight our metrics by the volume explored by the Rubin. This is by taking into considerations of the depth, footprint, and the star density. For the depth, some options at the observations in the short exposures, like the twilight one at short exposures at the cost of long exposures, while some options at the short exposures without impacting the long exposures, like the short to NS one. And our metric for the depth is the median of the signal to noise ratio to downweight the opsims with smaller observed volume, but reward the addition of short exposures to the survey. And finally, we reward the large footprint by counting the number of fields that's well observed. And we define the well observed as the field have the number of visits larger than the median of the baseline. And since we expect that more anomalies appears in the higher density regions, so we calculate the star density within the well-observed field as the last figure of merit to reward the observations in galactic plane. And the radar plot shows some of the best options under our metrics. Each corner represents one of the one element of the matrix, and the further outside, the better is the options in this element. And then in the right plot shows the opsims for all 100 opsims in the latest version 2.0 run. And under our metrics, the rolling ones, the 6 rolling opsim, and some rolling bulge performs the best because specifically they perform best in the color and the brightness change, because the rolling family improved the diversity in time gaps, and the rolling bulge add observations to the galactic bulge, so it has performs better at the star count metrics. And the NES1 increase the footprint to the North Hemisphere, therefore also ranked higher. And the baseline 2.0 is not bad, and it has been much better than old baselines. And from this plot, we notice that nearly all families of opsims have some good and some bad implementations. This means that implementation details are as important as high-level strategies. So after that, we move to the proper motion part, and I'd like to invite Fabio to present for us.
Yeah, I will take it from now. So along with the analysis of the anomalous variability that Xiaolong introduced to us, we expect also the ability of LSST strategy to discover object and structure in anomalous motion. We name anomalous to compare them with the theoretical description existing in the literature. For this part of our work, we had to move away from the completely model-free considerations, and we simulated proper motion of galactic stellar population as well unusual proper motion population, and applying the filtering criteria to see if we can measure with enough accuracy the proper motion to separate the unusual population. So we created three metrics to answer the following questions. What is the fraction of the unusual population that is identified as an anomaly in different opsims, given the measured proper motion of uncertainty? Sorry. The second question is, what if, and this is expressed by the likelihood score metric. The second question is, what is the fraction if the objects are also variable in flux? And this is what we measured with the
Fabio,
proper motion.
excuse us just a second.
Yes.
For whatever reason, when you started sharing slides, you're not advancing. Maybe you'll have to tell us.
Yeah, I'm not advancing. I'm still in this in this very slide. I will ask Xiaolong to move slides. Sorry for misunderstanding. I was showing. I was speaking out for the with respect the flow chart on the left of this slide. So at the bottom of this flow chart, there are these three metrics. So each of these metrics answer to one of the questions that we wanted to answer. So the first one from the left, the fraction of detected unusual, will answer to the question, what is the fraction of unusual population that is identified as anomaly in a different opsim given the measured proper motion uncertainties? While the second one answers to the question, what is the fraction if the objects are also variable in flux? And the third one, the confusion index, it answers to the question, will we be able to distinguish between different structures in a galaxy measuring the proper motion? So in the picture on the right, I show the distribution in magnitude and proper motion of the simulated object. To each object simulated, we associate coordinates, magnitude, and proper motion, and the distribution is one on the right. Next slide, please, Xiaolong. So first, we simply test the ability to recognize an unusual object, and we identified as unusual all the objects that fall outside the 3 sigma limit of the measured distribution of the proper motion from the unusual the population, and this is shown in the plot on the top of this on this slide. The three panels show the average and the best performing pointing from the baseline footprint. The dot point in the panels show the unusual proper motion population, whereas the circle line show the 3 sigma limit from the usual population. So the unusual population inside the circle cannot be identified as unusual, whereas the points outside the circle can be identified as unusual, and the fraction of those is shown at the bottom of the panel. The histogram on the right shows the distribution of values of our metric, the percentage of unusual object identified as anomalous, overall the footprint for the particular opsim. Then we moved to by adding a flux variability to each object. And what we measure, yes, thank you. Can you stay on the previous slide? Yeah. And what we measured adding this flux variability is shown on the in the bottom right plot of this very slide. The variability we simulated is a simple triangular shaped light curve that go on and off randomly through the survey time with a linear rise and fall. The magnitude, the impact, the number of detection for each object, and the signal-to-net ratio, the proper motion measurement. So we measure the fraction of transient with the measure of proper motion, and it's shown in the plot that I was indicated to you. The top panels show the distribution of the recovery rate, transient recovery rate, and the bottom panels show the cumulative fraction of the histogram itself, measured for each OPSIMS in the version 2.0 simulation. Next slide, please. Finally, we assess the ability to distinguish between structure with different proper motions, such as streams. We're using the Sagittarius A as a toy model and considering two cases. If Sagittarius A distance were increased, how far could we identify as a stream, and how much fainter could the Sagittarius A for us to still identify as a stream. This is that we analyze and then the uncertainties in the reduced proper motion diagram, and we measure the number of objects in diagram that fall in the error ellipse of each detected point. In this slide is shown the reduced proper motion diagram. There is the diagram, there's a plot that show the AG parameter that follow the equation in the bottom right, and the color. In the two rows show are four panel each, and each panel is an OPSIM. The top row show the case in which we made the Sagittarius A fainter, and the bottom row is the case in which we make it more distance. And the color is color coded for the fraction of object inside the error ellipse, which is the confusion index we were talking about. Next slide, please.
5 minutes, Fabio.
Yeah, okay. Finally, the ability to detect proper motion anomalies should scale with the number of objects observed. So the last, we added to our metrics the last piece, that is the star count. As shown by Xiaolong, we also converge all the information in the radar plot as with the bar plot, where the metrics are split by metric family, and for each OPSIM family, the OPSIMs are sorted by our figure of merit. Due to the metric design, the likelihood score is strictly correlated to the proper motion uncertainties. So strategies that enhance the number of revisits in the same night help to highlight very rapid astrometric changes. However, the trade-off between the filter distribution and the revisit time in the same filter and in the same field play a fundamental role in the number of measurable proper motion, because longer gaps in the same field, in the same filter observation give higher uncertainties, which lead to lower probability to identify a motion as unusual. As for likelihood score, also the transient proper motion metrics show better performance from OPSIM, which have more number of revisits in the same night, because these help to detect photometric variability. And finally, the confusion index appear more homogeneous among all the OPSIMs, as it has lower correlation with respect to proper motion uncertainties and a higher correlation with the depth and the resolution we measure the motion. Thus, it is enhanced by strategy which eventually can resolve most start. Final slide. So we are open and looking forward to we're open for questions, and we're looking forward to shedding some light on the unknowns. Thank you.
Thank you for a very interesting talk. We have plenty of time for questions. No questions in the room. It was a very clear talk in that case. I apologize as chair. I don't have as a session chair, I don't have a question in my pocket. So if we have no questions in the room, let's check online. Sorry, I'm not good at checking on Zoom. Do we have questions? Any hands up? No, all's good. Oh, we have a question.
So one of the fun things we could do potentially with other instruments, if we're not just using LSST for following up, is look in a different set of filters than just the UGRIZY for LSST. Is there some way you can answer the question of, given some set of anomalies that we are looking for, what's the most, should we start looking in narrowband filters for really unusual things, or should we use an extra wide VR filter, sort of like Kepler or TESS? Will that help us in any way? How can we enhance anomaly detection if we use multiple facilities, essentially?
Okay, yeah, very good question. Like for the LSST, we have only 6 features. Like therefore, the color is explored by only combination of two features. If we have other facility available, it will be a very interesting to look at the explore other combinations combined with features from other facilities to consider the measure of color and brightness. This might be a interesting project to look at.
Great, thank you. We have another question.
Hi, really great talk. I wanted to ask if you were asked to recommend, I don't know, 1 or 2 OPSIMs, which ones would you recommend that would be, like, in your opinion, best for finding the unknown unknowns?
Okay, from the result from considering only the time domain, we will recommend the rolling one, the 6 rolling, the strong rolling cadence ranked very high. Right. The rolling one from the radar plot, the rolling one perform best at color brightness, star count, and also footprint, but at the cost of some depth. So if we could improve the depth of the rolling one, this would be our best option to recommend.
Thank you on behalf of Gautam for making his day. We have Fred with a question.
Just before anybody gets too excited, I want to point out that the 6 rolling cadence, that 6 stands for, like, you would have 6 bands on the sky and you would roll them. So it's a very aggressive rolling that breaks a lot of other sciences. So don't, and I'm on this paper, so, you know, like, I agree with Xiaolong that for this, that's what we would recommend, but that is a very unlikely strategy to happen.
Thank you for that clarification, Fed. It's very reassuring. Any other questions? Do we have, I know we just have your comment being recorded there on Zoom, okay. Looks like that's it then, folks. So let's thank our speaker again, our speakers.